Hello friends, welcome to lecture number 5 of first chapter of class 12 NCERT physics, that is electric charge and electric fields. So in the last video we have already discussed about electric dipole in an uniform magnetic field. So in this video we're going to discuss about electric flux linked with a surface and linear charge density, surface charge density and volume charge density. So hope you're gonna like it, and if you like it, just hit the thumbs up button and share with your friends. And if you are new to my channel, please subscribe the channel and inspire me to create new contents for you. So now let me take you to my screen. So let's start. So first let us discuss about electric flux. So what is electric flux? Total number of electric field lines passing through a surface normally, okay, that means perpendicular to the surface, so is the electric flux linked with that surface. Okay, so given by phi, electric flux, electric field E into S is the surface area. So this is the surface area and these are the electric field lines suppose passing normally through this surface. Then phi is equal to E into S is the expression for electric flux through this link with this surface. So now let us consider this is a small surface element and its vector is towards this direction. Okay, represent this S is equal to the surface area and E is the electric field here, and S vector represents the area vector which is normally outward from the surface. So now you see, what if the electric field lines are inclined to this surface which makes angle theta with this area vector, this area vector S. So angle made by the electric field lines with the area vector be suppose theta, then what will be the expression for the electric flux? Now electric field lines are passing through the surface of area S such that angle between E and S vector is theta suppose. Then electric flux is given by, so here you see, so electric field lines are not passing normally now, it's they are making angle theta with the area vector. So that's why we're going to take the cos component. Vectors can be resolved into two components, one is sine and another is cos, right? So here we're going to take the cos theta component, which one will be normal to the surface. Okay, which one will be normal to the surface? This is electric field line C and this is the component, and here you see, so this is E sine theta and this which is along the area vector S, that component is E cos theta. That's going to be to the perpendicular to the surface, so that's why we're going to take that component. So hope you have understood this. So now this is the expression phi is equal to E S sine cos theta to which gives the electric flux linked with the surface if the electric field lines pass through it makes an angle theta with the area vector. So hope you have understood this. Now phi is equal to E S cos theta if theta is equal to 0 degree. If theta is 0 degree, theta is 0 degree means electric field lines are parallel to this area vector, that is perpendicular to the surface. Then cos theta we know 1, so then cos 0 is 1, then phi will be equal to E into S, that is maximum flux. If theta is equal to 90, that means this E field, electric field, is perpendicular to the surface area vector S. Area vector perpendicular to the area vector means it is parallel to the surface, okay, not perpendicular to the surface. So then here you see, this is your area vector S, and here this blue colored lines are the electric field lines. So that is the meaning of theta 90. So then cos 90 0, so flux will be 0. So here is the flux minimum. So hope you have understood this. Now electric flux is a scalar quantity. Remember this, it is a scalar quantity and its SI unit is Newton meter square per coulomb, or you can say joule meter per coulomb. So hope you have understood this. Now dimensional formula of this electric flux is this is the dimensional formula. So hope you're gonna remember this. Now let us discuss about let us consider an irregular surface like this over which electric flux varies. Okay, so we have considered an irregular surface as shown here. So ds be a very small area element. Let us suppose ds be a very small area element and ds vector, area vector, this red color part. So this is the area vector, suppose ds vector, and E be the electric field which makes an angle theta with the ds. Okay, so E cos theta components of E vector perpendicular to the surface like this. We have considered these are electric fields, and this is the ds, that is area vector, and this is the angle theta, suppose. Then electric flux through ds is given by d phi is equal to E cos theta ds, right? So you know cos component is the perpendicular component which is normal to the surface. We have already discussed about that. So here d phi is the electric flux. This d phi is the electric flux linked with the small area element ds, right? So then eds cos theta. So eds cos theta, we can write that E vector dot ds vector, right? This is dot product of two vectors, right? Because E dot ds vector, that's gonna be E ds cos theta, because you know vectors, suppose we have a vector and b vector and their dot product is given by ab cos theta, right? If you compare with this one, then you will get this E dot ds. So hope you have understood this. Now total flux. So to obtain the total flux through the surface, that's phi, can be obtained by integrating d phi. Okay, integrating d phi. So if you integrate this, then you will get integration E ds cos theta, integration E dot ds, right? So this is the expression for total electric flux through an irregular surface, right? So hope you have understood. Now let us discuss about continuous charge distribution. Okay, continuous charge distribution. So it is nothing but a system of closely spaced electric charge which forms continuous charge distribution. Okay, so now linear charge density. Let suppose this is a line we have considered, and charge are distributed uniformly over it. Then so q charge, total amount of charge distributed over it, suppose q, and here you see length is suppose l, then charge per unit length. So when is the uniformly distributed, when charge is uniformly distributed over a line, we call it linear charge distribution. This is linear charge distribution, and here you see, suppose q amount of charge is distributed uniformly over it, then l be the length, then the linear charge density is given by lambda, that is q by l, that means charge per unit length, and this is the SI unit, coulomb per meter. Okay, coulomb per meter. So linear charge density is the charge per unit length. So hope you have understood about what is linear charge density. Now let us discuss about surface charge density. So when the electric charge is continuously distributed over a surface, when then we call it surface charge distribution, and if q amount of charge is distributed over a surface of area S uniformly, then the surface charge density is given by sigma q by S, that is charge per unit area. So SI unit should be coulomb per meter square now. Okay, coulomb per meter square. So hope you have understood. So surface charge density is nothing but the charge per unit area. So hope you have understood. Now volume charge density. So volume charge density, when the charge is continuously distributed throughout a volume, then we call it volume charge distribution. And if q amount of charge is distributed uniformly throughout a volume V, suppose, then the volume charge density is given by rho q by V. So SI unit will be coulomb per meter cube, because charge per volume now, right? So therefore we can say volume charge density is the charge per unit volume. So hope you have understood this. So if you have understood, please share this video with your friends, and if you like the video, hit the thumbs up button. If you are new to my channel, please subscribe the channel, inspire me to create new contents for you. And thank you for watching. See you in the next video.